Hello and welcome to a video on difference amplifiers. So in this video we will be looking at the derivation of a difference amp, the design, then some simulations to make it a bit more visual of what's going on. Then we will discuss differential mode, common mode, and the common mode rejection ratio. And lastly again, a problem for you to work on and also to simulate. So, the difference amplifier is basically a subtractor. So, voltage 1 and 2 is being subtracted from one another and amplified. So, let's look at the derivation. So, first off, the normal assumption that the two currents flowing into the amplifier is 0. And then the rest we can solve using superposition. So, if we ground V2, we have a look at V1. We will see that with this terminal at V2 grounded, basically through the amplifier, since there is no current flowing through these resistors, this point is 0 and also this point is 0, making our output for V1 just the inverting amplifier configuration. Okay, so that's the first part of superposition. Secondly, we ground V1 and have a look at V2's input. When we ground V1, this top side here, we're taking VP as the input of our amplifier, is a non-inverting configuration. And the two resistors R3 and R4 is just a voltage divider. So the voltage at VP is the voltage division of V2, and the input here is just non-inverting configuration. Okay, so VP is being amplified and V2 is being voltage divided. If we add all of these equations, we find this one here at the bottom. Okay, so that is how we find the equation of the difference amp. Now, there is some special cases to this, and with the cases, we can look at some designs. So, taking this formula, if we want different ratios of the two being subtracted, we can make it from this formula. So let's begin with choosing resistor 1 and 3. Resistor 1 and 3 is the input resistors. So typically you want the input resistors to be the same value. So we choose them to be the same, and the input impedance of a difference amp is the sum of these two resistors. So the differential input here is 20 kilo ohms if we choose 10Ks. So from this equation, the minus 10 can be equated to minus R2 over R1, and the 4 can be equated to this monstrosity up here. Note that the positive gain must always be smaller than the negative gain, or else your equations will never work out. So just note that this gain here must always be larger or equal, or else it won't work. Mathematically, you will get negative values and stuff that don't make sense. Anyways, so plugging these two in, we find that resistor 2 should be 100 kilo ohms, and then we can solve the positive half. Since we already have R1, R2, and R3, we only have R4 left, and this works out at roughly 5.6 kilo ohms if we need to choose the E12 value. And there we have realized this equation and designed the resistors. Case 2, the one that we will be using as our example later on. we want a similar gain and the subtraction of the two values being inputted. So again, we can choose R1 and R3 the same value, keeping the input impedances the same. And we can set R2 and R4 the same. So by doing this, our equation changes so that this top half here and this bottom here cancels one another. And with a cancelling, we have R2 over R1, and here we have R2 over R1, giving us a similar resistance ratio for both sides, and then R4 also becomes 100 kilo ohms in this problem. So this is kind of a simple, straightforward design. Choose the resistors to be the same, and finished. Okay, the third case is when you want straightforward just subtraction with no gain. You just choose all the resistors to be the same value. Everything will cancel out and you will have V2 minus V1 left. So let's go and look at some simulations of these three problems. So I went ahead and set up a simulation for the first case that we had, where we wanted 4 times V2 subtract 10 times V1, and I input two 1 volt sinusoids at the same frequency. So if we run the simulation and we check these two voltages, they are both in phase with one another and both have amplitude of 1. And if we take the output, it should be minus 6 volts. So that means that the signal should be inverted and with an amplitude of 6. So with this configuration, our amplifier is actually working. Now, for the second case, this resistor was 100 kilo ohms. So if we would run this, our output would suddenly be very small in comparison. But the gain for both sides should be 10. So this means both of these signals have been subtracted from one another, and there is a bit of a remainder left on the output. We will have a look at what's going on here with common mode in the next section, but we can see that the subtraction is happening, but there is still a bit of a remainder. Okay, let's make this maybe 2 volts, and if we run the simulation now, our output is saturated because I'm using a practical op amp here that I included. Let's make this a bit less. 1.5, run it. Our output should be 5 volts. So 1.5 minus 1 is 0.5 times 10 is 5. So there is our output. So our subtraction is kind of working. Okay, so it's kind of fun to play around with this. And the best way to learn simulation software and the actual circuits you're working with is to put them in a simulator and just play with it. You'll understand more about the components and what changes they bring if you just play around. The answer to this should be 0.5 volts because this is now case number 3, and there we have it. Okay, so I'll put this simulation also on my tutor with the rest. So let's jump back and look at the conditions that we have also seen while playing with this amplifier and some analysis tools that goes with it. So one of the many terms that you will hear a lot is differential mode gain. And that is when we connect, let's say, a sensor into our amplifier like this, and there is clearly a difference between the two. And the thing is, what is the gain when we do this? Okay, And with a selection of R1, R3 being the same, and R2 and R4 being the same, we have a case, the second case that we had, and this is the differential mode gain, is when we combine those two into one factor. So the differential mode gain is just the ratio of the two resistors. Okay, so the gain that we selected. So differential mode gain is the amplifier's amplification capability. Okay, so if we put in a signal, how much will we amplify it? Okay, the second term is common mode gain. Now we saw this in the simulation when we connected the same kind of signal into the inputs like this, and our answer was or should be 0, and it wasn't because I wasn't using a perfect op amp to begin with. And one of the other factors is resistor tolerance. We don't have perfect resistors when we build things, so if we input a perfect signal, the result will not be 0. Okay, in any ideal case, the common mode gain will be 0 because output voltage divided by this common mode signal should give us a 0 result. Okay, so due to the tolerance, this is not 0, but your common mode gain should always be between 0 and 1. Okay, if it's above 1, it's a big problem. If it's between 0 and 1, it is an attenuation, not a gain anymore. Now, this common mode gain gives us our amplifier's ability to reject noise. So if we insert a common signal, they should be subtracted as much as possible. So if a cable is running through a factory and one carries a signal, one is the ground, or whatever it might be, both will pick up the same noise, but one is carrying the signal. So the signal you want amplified, and that is the differential gain, and the noise that's running on both you want subtracted, and that is the common mode gain. Okay, so the one you want amplified and the other one you want reduced or attenuated. So the common mode gain is described by this equation down here. So again, the voltage division and then some ratio of the gains. If you supply perfect resistor values in here, this will result in a 0. Okay, but we can use this with our resistor tolerances to find the worst possible common mode gain. Okay, this brings us to common mode rejection ratio. This is when we take the differential mode gain and the common mode gain, divide them, and put it in the decibel scale. This is just a nice way to tell us how much noise reduction we have. So the common mode rejection ratio in our amplifier. So on to the problem that I hand to you, so you can pause and try and solve it, is to take the second example that we did and assume that all the resistors has a tolerance of plus minus 5%, and I want you to calculate the worst case common mode gain and then the common mode rejection ratio and simulate the results. So I want to know how bad, with a similar input signal, how bad this output could be. So pause and go and try it out. And you need to use this equation here with the resistor tolerances. So the first thing that you're trying to do is you first need to maximize and minimize this entire equation. So the best way to do this is first try to find the small values on top here with the biggest values at the bottom, and then vice versa, and you will minimize and maximize this equation. So take our 10k values and we add and subtract 5%. So for R1, if you want to maximize first, this goes bigger, R2 goes smaller, R3 goes smaller, and R4 goes bigger. So this minimizes this term, maximizes this R1, and we will find the first maximum. Then we just swap the values out to do the minimization, and we will find our minimized terms. So the common mode with the maximized values, we find 166.4 millivolts per volt and almost inverted 200 millivolts per volt for the minimized terms here. Okay, and then I took a absolute average of the two, just to show you that this will kind of average out to this value in general. But this highlighted one here is our absolute worst case scenario for common mode gain. We will have a look at that in the simulation. I also use the same resistors for the differential mode to see that the minimum and maximum that you will get for maximized and minimized values is you will have a lower gain and a higher gain, and in general this will average out for your amplifier. So this is the two horrible scenarios that you can get, but in general it will go to the 10 that you designed for. So you also use the 10 that you designed for in your common mode rejection ratio. So the one that you typically want as the answer is the one that is with your worst case scenario common mode gain. So 34 decibels is our worst case common mode rejection ratio. And you'll see that the common mode rejection ratio is higher, where our common mode is less, and it's even better right here. So the higher the common mode rejection is, how better noise is rejected, and the lower it is, how much worse noise is rejected. So much noise will pass through a system. So common mode rejection ratio, big thing when talking about medical equipment. So this value you want typically 80 dBs, 100 dBs plus, infinite if you can, but that is not possible with practical components. But that is what you're aiming for. So better CMMR, and you will be good. So let's go and have a look at the simulations for this. So first I'm going to show you the differential mode. So I just set up a signal in between the two input resistors here. And let's amplify this. 100 millivolts should become 1 volt. And there we have it. So don't need a ground here or whatnot. You can connect the signal like this. And there is our differential mode, and it's the resistor ratios like we had them. Okay, the more fascinating simulation is the common mode. So I'm going to go over to that quickly. So I have everything set up for the common mode here. So the differential we already know is 10. I put in a 1 volt peak signal in 1 kilohertz, and these are the resistor ratios for the two different cases that we have. So let's first run it with perfect resistors, and we see that this is 400 micro volts with a bit of offset. Remember, this is not ideal op amp I'm using, so I'm also going to see offsets. And we have this signal coming out, but it is very small. Okay, so from 1 volt to 400 microvolts, it's kind of a good noise reduction, um, like that. So always try to match your resistors perfectly when building this so that common mode signals are well rejected. Okay, so let's change the resistors in here to match these quickly. So I changed the resistors quickly. I missed a K here. I changed the resistors quickly and let's run the simulation. And like we calculated it, it was about what, 166. Where is this cursor? Here. 166, and here we have it, 165. Okay, so the first case is not the worst case. That's where we minimize the values. So it works out perfectly. Let's look at the second case. So adding a 1 volt signal, getting the output, you can calculate your common mode common mode directly. So there we have it. Quickly going to change the resistors again, and I'll be right back. Okay, so here is the worst case resistors locked in. Let's run the simulation. And this is at almost 200 millivolts peak. So that 200 milli, or we select this input inverted 200 millivolts peak. So 200 millivolts per volts on our common mode. So if we insert a very large signal like this, say it's a 50 Hz signal from a power line, we will still have a 200 millivolts of that signal passing into our system through our amplifier. So this is really bad. Okay, so when building this, rather use 1% resistors, measure them beforehand, try and fix them before, and your common mode will be much less. Okay, so noise suppression will be much better. Okay, and that is it for our difference amplifiers. Thank you for watching, and see you in a next video.